Okay. Hello, my name is Danny. I'm a machine learning engineer in Dessa, and today I'm going to talk to you about Google BERT. State-of-the-art pre-trained model using a completely novel architecture that achieved great results on various NLP tasks. Okay, so where do we begin? We first have to ask ourselves, what's the purpose of the BERT paper? So I want to start with learning language representations. What is the idea of learning a language representation? Well, it's often done by representing a word with a learned embedding vector. And the most common one here you've all heard of is word-to-vec. And as you can see here, here's an example that the meaning of the word is captured in the geometry of the embedded vector. See, the difference between king and queen is equal to or similar to the difference between man and woman. So there's that intrinsic meaning that is captured in the embedding. Now, word-to-vec is very useful. It's very useful into our day-to-day lives because it allows us to craft meaningful representations about words that we can use in our models. Let's take it one step further. Let's build a general, pre-trained language representation model, such that this model can adapt to various NLP tasks easily. And we don't have to retrain a model from scratch every time we want to do an NLP task. Because a lot of these tasks have things in common, such as understanding words and sentences. This idea of how? Well, this is what the authors tackled. So what was the motivation behind BERT? Well, I'll share this quote with you from the BERT author. For several years, people have been getting very good results pre-training deep neural networks as a language model, and then fine-tuning on some downstream NLP tasks, which have it question answering, natural language inference, sentiment analysis. So this was the motivation behind BERT. Now, I want to just go through a little bit of the history of neural language models. You've all heard of CNNs and RNNs. These are models that take in an input sequence and then go through it sequentially. Now, as my colleague Joseph Palermo of Dessa, as he said in the meetup 2 weeks ago, attention is all you need. I don't know if any of you remember that. The sequential computation makes it difficult to learn long-term dependencies. And it's also difficult to parallelize too. So there's an added cost of computation on top of that. So what was the solution that he presented? Well, it was a transformer. In 2016, a new mechanism called attention, or rather self-attention, allowed models to give long-term dependencies easily to words in sentences. Now, when you learn representations of these words, they can learn relationships to all of the words in a sentence, and you don't suffer from that loss of a long-term dependency. And this was very parallelizable, and it completely replaced recurrence and convolution. In fact, if you look at a lot of the current NLP models, they're all these type of massive attention models. Precisely one of them is the Bidirectional Transformer, BERT. So last month, October 2018, the Google research team came up with BERT, and pre-trained bidirectional, I'll explain what that means, transformer that can be finely tuned to many NLP tasks. So what is BERT? Now, it stands for Bidirectional Encoder Representation Transformer, but I don't really understand what that means. I just think it's a very nice, I didn't think they thought of the acronym first and then filled in the words. Well, first of all, the first word is bidirectional. So BERT is naturally bidirectional. And this allows for the best contextual representation of the word in the sentence, as you will see. It's also generalizable. What's the whole point of BERT? It's a pre-trained model that can be finely tuned easily and inexpensively, meaning only very few new parameters to be learned, to a downstream NLP task. Think question answering, natural language understanding, things like that. High performance. Once BERT is finally tuned to NLP tasks, it achieves state-of-the-art results on a variety of NLP tasks. So beating the status quo. And finally, universal. I added this one myself because I thought it was very interesting. Is that BERT is trained on plain text. It's trained on Wikipedia and book corpus. And by when I say Wikipedia, I mean Wikipedia, like all Wikipedia, all 3.5 billion words. And there's no special data set that is needed. And the reason why this is important is because you don't have to hunt for a nice data set to train your model on. You can use any text relating to a language. So this generalizes very easily to other languages as well. In fact, 3 days ago, Google Research released BERT Multilingual, which does what BERT does, understands languages, but understands a variety of languages. They also released BERT for Chinese, which I thought was interesting.
Can I ask something here?
Yes.
So about the generalizability, sorry. So that word easy, did you say easy means that it has only a few parameters to tune, or what does it mean?
So easily means that you don't have to, it means a lot of things. It means you don't have to completely rip apart your existing model architecture. The authors promise that you can only add one extra layer and learn a very few amount of parameters to achieve excellent results. So that's what it means by easy. Any other questions, clarifications? It's only questions that can be accepted, fortunately. So, so before I want to discuss what BERT is, I want to review a little bit of transformers. Now, I assume you guys are all experts in transformers after my friend Joe's talk on transformers. But for those of you who missed the talk or who weren't listening, like me, here's a little bit of review. What is the key to success of the transformer? Well, it's the idea of self-attention, right? What was the problem with RNNs? Sequential processing makes it difficult to learn long-term dependencies, long-term relationships. Let's say I want to understand this sentence here. The animal didn't cross the street because it was too tired. What does it refer to? Obviously, we can do some analysis and we say, well, it refers to animal. But that's quite a difficult task for an algorithm, for a machine learning model to learn. What self-attention does is that it allows words to learn relationships with all other words here. So that using self-attention, the model can learn that it here has a very strong connection with animal. And that helps the model learn a representation. And the reason why this is important, that self-attention allows it to learn from all parts of the sequence, is that now the model can output the best contextual representation of the word. Right? Not something that just looks at the word it for word to vec, or looks at the preceding couple of words as you would for a sequential model. It knows the best contextual representation, the most holistic representation. I just want to talk briefly about the types of attentions that are used. Now, again, this will be a lightning review in order to save time. Transformers come in an encoder and a decoder. So imagine here that the encoder deals with a French sentence, and the decoder deals with the English sentence here. Je vais bien, and the translation, I am well. Encoder or decoder attention will mean that the decoder input, the word am, will try to learn relationships to the encoder input, je vais bien. The decoder self-attention, well, it's attending to itself. But the decoder self-attention, as you are generating these words, I am well, step by step. So in order to avoid some type of leakage, you only can learn relationships with words that came before it. And that's a very important point, right? For example, I can't learn any relationship because it's the first word. Am can only learn an intentional relationship with I. And well can learn with am and I. That's for the decoder. But for the encoder, it is not the same. In encoder, you see here that all three words here can learn relationships all with the other words. Shvabien can learn any of the connections here. I just want to let you think, this looks like something that's roughly by directional.
Oh my god.
Keep that in mind. There's a lot to take in this graph. This is a review of transformers. So let's begin here with the encoders. Forget about the decoder. I'll block it out for myself. So the encoder input is, here it's a sequence thinking machines. Right? So there's two words or tokens to this, thinking machines. They first put it through that encoder self-attention that you saw in the previous slide with lots of connections. This add and normalize layer, that means that this connection is a residual connection. It just makes it easier for the model to learn the signal. Then it's passed through feed-forward networks. Each word itself is passed through a feed-forward network that also has a residual connection. And you do this, and you just multiply it by however many encoders that you have. And as you see here, we've done away completely with recurrent layers, with convolutional layers. All we need is this encoder self-attention layer and straightforward feed-forward network, feed-forward layer. Now in terms of decoder, it's much of the same. So the decoder input here is going to go through a decoder self-attention, which is similar to the encoder self-attention, except that it can only look at tokens in the past. Right? It can't look at tokens in the future because they haven't been generated. Right? And then it goes through much of the same thing as the encoder block, with one other notable exception, is the encoder-decoder attention, the one we saw here. Now the decoder representation here will interact with what comes out of the encoder. Right here. And so imagine the encoder output then interacts with the decoder, let's say, middle result, this decoder result, in that encoder-decoder attention. So this way, they interact with each other at every step of the decoder. That's a very basic overview.
Actually, what is the input to the decoder?
So the input to the decoder, usually in the frame of machine translation, which is what the original paper was about, is that you would have your original sentence, let's say French here, je vais bien, and then on the decoder output, you would to train it, you would insert the steps, the translated output. I am well, one step at a time, and try to have it generate the next output at training time.
Yeah, that's correct. So basically, you just fit your French sentence, and then it will create the first character, like the first symbol for the output. And then you run it again, and you feed in the first output in the decoder layer, and then it will give you the next character. And the last character will give out, it will be the stop sign.
Yeah.
And then then you just stop.
For example, here, je vais bien, you will put that on this side, and then here you have the start symbol. It will predict hopefully I, put that back in, and put that back in, and well, put that back in.
So
And then well would generate stop, ideally.
the thing is like limited. So BERT has 512 characters positioned for the input. So let's say you want to translate a sentence with more than 512 words, which is very unlikely, then it wouldn't work. You have to chop off the sentence. And the thing is that with the stop sign generation is important because depending on the language, your output sentence might be longer or shorter.
Yeah.
So I guess a very short summary. The inputs are the encodings from the inputs to the decoder. The encodings from the encoder are the outputs of the previous time steps of the decoder, and the attention from the encoder that you see comes in later on.
Yeah, transformer is pretty complicated. Huh? In fact, in my opinion, BERT is a simplified version of a transformer and consists only of this. But I'll explain what I mean. Okay, moving on. Bidirectionality. Here's fine now. So language models are typically unidirectional, meaning that they are either left or right or left. Okay. Like RNNs. The thing is, it doesn't make a lot of sense because most NLP tasks just want the best contextual representation of the entire word. And you should see everything to the left or right. Right? So I've been saying this word contextual representation. I'm saying context a lot. But what does it mean? Let me give you a concrete example. Context is everything. So say we had a no context representation, like word to bank. Then in this case, the bank and riverbank and the bank and bank deposit, which are clearly two different meanings of the word bank, will be mapped to the same representation. And you can see how that might be a problem in understanding language. Right? If you have a left to right context, or a left context, R and N, if you wanted to analyze, if you wanted to make learn a representation of bank in the sentence, I made a bank deposit, well then, the R and N would only consider I made these words before bank. Finally, what we want is a bidirectional context. When you have the sentence, I made a bank deposit, it should learn the representation of bank from all of the words in the sentence. I made a deposit. Not just things to the left, not just things to the right, but everything. And that is at the core of what BERT is. This idea that bidirectionality gives the best context. So how do you make a bidirectional model? Well, here's an easy hack. Just make a left to right model and a right to left model and add them together, or concatenate, such as Elmo. But the problem with this is that, first of all, it's kind of a hack, and second of all, it's what was considered shallowly bidirectional, in the sense that you train this left to right and you train this right to left, and you only add them in at the very end, and maybe a couple extra layers. Right? It's not bidirectional from the get-go. That's what BERT attempts to achieve. A naturally and deeply bidirectional model, right from the start, using the power of self-tension, and by the power of that specific type of self-tension that we saw. Do you remember what type of self-tension it was? There was encoder, decoder, there was decoder, there was encoder.
Encoder?
Encoder, right. And why do we like encoder?
Because you know what's on the left and the right.
That's exactly right. Zane, right? There you have the encoder self-tension. In the sense, it's bidirectional, and it can learn relationships with all of the words in the sentence. And what BERT is, in essence, is that you take, the transformer block, which has the encoder self-attention, which is bidirectional, you feed words through it, and then you just keep going. So you just stack all these transformer encoder blocks. And that's BERT. Thank you very much. So each word and token goes through this entire stack, and a representation is learned. So the idea behind BERT is incredibly simple. Let's take a look at how the paper draws it as. So this is what the paper has. These EIs here represent each word in the sentence, gone through some preliminary encoding. and they're fed through this giant transformer beast, and at the end, the token, the first token, E1, is sent to the learn transportation T1. And this T2 is a learn representation of E2, and so on and so forth. Now this diagram is a bit confusing when I first saw this. Because when I first saw this, I thought that these were all their own transformer blocks. And then each token goes through its own transformer blocks, and they all talk to each other instead of weird attention mechanism. Right, no, that's not what happens. And I was disappointed to find in the source code that it looks something like this. But this diagram, all it does is try to stress the point that what the transformer is doing is that it is really bidirectional, right? It's not just one unidirectional. So that's the whole point of this diagram. If you ever should read the paper and get confused, that's one part that confused me. So from this,
It's just the laziest way possible to visualize the network.
Argumentative question.
that wasn't a question, that was just a statement. I think statements are allowed. So, model details. I'm just going to tell you a little bit, just some details about the BERT model. There are 4 of them: BERT base, BERT large, and cased or uncased. First of all, cased and uncased basically means that BERT treats lowercase and uppercase differently. And BERT base and large, why are there 2 models? Well, BERT base has roughly the same amount of parameters as a predecessor, OpenAI GPT. And they have first created BERT base in order to compare apples to apples with the predecessor. Well, not the predecessor, the leading model up to that point. And then they created a large model because it was fun, right? It's a huge model. And you imagine here that the layers here represent the number of transformer blocks, right? So if you imagine here, this is 1 layer, 2 layer, 3 layer, 4 layer.
So just to wrap my head around this, I just took a transformer and cut off the decoder part, stacked them together, and that's their paper?
Seems like yes.
Yeah, that's
it. Yeah. I guess to emphasize on the actual importance is that we didn't have transformer networks were there, but we didn't have embeddings from transformer networks. So I guess that's a more fair. Well, it was bidirectional. The transformer networks. That's my question, but that's argumentative. So I wanted to leave it for the second part. But yes.
I don't understand if you cut off the decoder how you train it.
Yeah, that's a great question. That's a great question. That's where I'm going to lead to next.
Okay, great.
I have to fetter that question. So this is the idea that, so 12 layer, 24 layer basically means the number of transformer blocks that you have. This is a hidden size within a layer. These heads represent the number of heads in multi-head self-tension, which is, I'll briefly summarize it, which is you do self-tension a bunch of times, and then you summarize them. And the thing I really want to show to you is that these are big models, right? 100 million parameters, 300 million parameters. So those are the model details.
To me, it's 768 hidden layers, or it's just hidden parameters.
Excuse me. I think this is a hidden size. 768 is a hidden size.
Oh, I see.
And that's a bit too much. 768 layers for each layer. Oof. Okay. Answer your question. How to train a bidirectional model? Unfortunately, it's impossible to train a bidirectional model like a normal language model, because it's the idea that since you have bidirectional connections, words will indirectly be able to see itself, and then prediction would become trivial, which is what the paper claims, right? And to do this, I really think that this is a very novel invention of the paper. You know, maybe the transformer thing didn't impress you guys so much, but maybe this will impress you. That they used 2 novel, unsupervised prediction tasks. And by unsupervised, it means that this prediction task is generated from a plain text corpus, like Wikipedia, like a book, a corpus of books, things like that. And that this can be generalized to other languages easily. So what is the first of these two novel and supervised tasks? Well, first task is a masked language model, also known in literature as the close task. The idea is that take an input, which is just a text sentence in your text, and you map out and you mask out about 15% of the input. Right? Its original sentence was, the man went to the store, he bought a gallon of milk. You mask out the store, mask out gallon, and the objective is for the model to try to predict try to find out what these masks are. Right? That's the general idea of this masked language model, and this teaches BERT to learn the contextual representations of these words in these sentences. Of course, the actual thing they use is a variant of the masked language model, a bit more complicated, and I'll refer you to the paper to find it out. But this is the general idea of the first of their tasks.
A question on the masked language. Did they use word level, or did they do it at the character level, or?
Oh, word level.
Okay.
Word level. So token level, right? These tokens that are being fed into BERT.
Use the word piece tokenizer. So it'll take a word like playing and divide that into two tokens. Play.
I don't think I understand how doesn't that become a supervised problem at some point?
Yeah.
It's not unsupervised.
Yeah, so
Okay.
unsupervised meaning that, I'm putting quotations, in that it generates a supervised task from itself.
Okay. How does the prediction, it's still confusing me that there's not a decoder part. Because I thought you needed the decoder after the encoder to be able to even get to a target at some point.
Right.
Like if you just cut it off an encoder layer, then, so did they train it with the decoder layer, but then they chopped it off for the representation?
That's a good question. So after it's being fed through all the transformer encoders, and experts feel free to help me out, it's then being, I had the same question myself, it's then being put through a couple of final layers, like a linear layer and then a softmax layer to be able to predict the models. And then they do away with that, right?
So they trained the whole thing as it was shown before with the encoder and the decoder and the softmax. In the end, there was a linear layer and then a softmax for predicting these labels. But now I'm thinking like, in the paper itself, they showed only like one output, right? One output token. And I'm not sure what they're going to do in those cases where you have like multiple tokens in one case, right? In one data point. So maybe they put out every token from the whole thing. And then they just do the softmax for every position, and then they say, okay, give me back. You need to recreate the whole thing.
Yeah, the key problem, as Florian mentioned on the Slack channel, is that the paper here is quite light on how it pre-train, on the details of how it does the pre-training. That's why they release a source code. Of course, you have to go through the source code and try to find out how it did that.
How many lines is that? How awful is it?
Well, it's written
one
pretty
awful.
well. It's written pretty well, but it's a lot of code.
I think the important point is that, and that was kind of raised earlier as a question, you have multiple masks, and those are your targets. You either want to predict one of them or all of them simultaneously. It seems that Florian mentioned we're not sure if we're predicting them together or one by one. If you're taking 512 characters or words in, then you're probably doing it together, but for each one, you're only looking at, if you're predicting mask 1, for example, you're only looking at the context of the sentence of mask 1. So you're only looking at that sentence. So for each sentence, technically you have one target to hit.
Oh, I don't know about that.
There can be multiple masks in each input sentence. They mask 15% of the words.
I think that wasn't shown over there. So if there are more than one, then you predict both at the same time, or yet we don't know.
That should be the case.
Can you input multiple sentences? Is that what you're saying too? Because the sentences might be related to each other, or not? Because then the structures get all.
The input sentences can be multiple. They call them sequences. They can be multiple sentences, and they mask 15% of all the tokens in the input, so there can be easily more than one mask tokens. Yeah.
Okay. Then you'll have to have two softmax nodes if it happens to be two, for example, in one sentence.
Yeah.
You could have multiple, but could it be that they just do one at a time? They can mask multiple out, but then just do each task one by one. And that would make it a lot easier. It would be an easier problem to solve than trying to predict all of them. But they might predict all of them.
Yeah, but they say 15%.
Yeah, it seems like.
So what I think is maybe, I guess they, like I said, they do the soft prop thing, right? So they look at all the input, and you just predict the token, and then when you predict the first token in the sentence, you just take the output from that model, and then you go and predict the next token. You just continue until you have predicted each token in the sequence, and then you go to the next data point, basically, and then do this over and over and over again. So they mask these. Let's say you have a sequence of text, like 2 sentences or 3 sentences, and they mask 15% of all the words. And then they just try to predict these 15 words. Because there's no point in predicting the. If your input contains the, you know it's the, you will not learn anything. You just learn uniform transformation. Right. So basically, you just predict mask 1, and then you know mask 1 already. You have your output from the model, right? And then you just predict again mask 2.
Yes.
Can we go back to the slides that you explained that the structures? I wonder that how many you have hidden layer here? How many hidden layer we have?
Hidden layer refers to this one. Also,
in the board you have the slides. You wrote that number of the nodes and number of the hidden layer, hidden size.
Ah, this one, yes.
Okay, so now you mentioned about the 12 head and 16 head.
Yes.
As far as I remember, in the transform learning, the paper, if I'm wrong, please correct me. It has 8 heads, and then you mentioned about that 8 heads basically is the size of that, how far you are going to look, or how in the case of bidirectional, how back you are going to look. And then if that was the case, then the window size here is 12 or 16.
The heads here refer to the heads of the self-attention. So that's a parameter of the self-attention.
Then means that I can put my attention 12 word next to the place that I'm looking right now.
No, that's not what the heads here mean. So in self-attention, you learn relationships to all the words, all other words in a sequence. And heads here just means that you can think of it as how many times you do self-attention. The more times you do it, you get a more robust result.
So heads are essentially, like the number of heads is essentially the number of types of relationships that you learn. Mm-hmm. It's like kernels in CNNs. Right. So essentially 12 heads doesn't mean you're interacting with 12 words. It means that you're learning 12 types of relationships in like the whole words. Right. So I'm going to argue about the question that Harriet was asking. If anyone else is confused about that, watch the 2 attention videos coming up soon, because a lot of this is like what you're asking is discussed in those 2 sessions.
I think it's out.
Is it out? Okay, it is out. Sorry.
Any other questions? Back
There
to
was here. Do you have a question?
Yes.
Yes, for the masks selected, is it a random?
Random, 15%.
Random selection, and will a sentence only be seen once with a random mask generated from the sentence? I guess it's this, or would it use the sentence again with multiple masks applied to it?
Oh, I don't know about that. My guess would be only once. We had to look through the source code. That's my guess.
I think they did 2 epochs, so you see the sentence twice, 2 or 3 epochs, something like this.
Can you learn representations for words that are not the masks, or
So
you
if
only
do
learn
2 epochs,
embeddings for the words?
Oh, well, you
that are
learn.
selected for
The idea is that you learn representations for everything, and then so that's BERT model. And then at the end, how do you get these representations to actually learn the model? Well, you attach a final layer to that does this task, and that way, everything up to here is learned. Right? So you chop out the final layer, which is what you do.
So if a word was not present in Wikipedia or whatever the other
book corpus?
Yeah. Then you're out of luck?
Well, they use the word piece word vectors, and that's their input word embedding.
Yeah.
So it's, I think, perhaps more based on that vocabulary as well, or at least the intersection of those two.
They have some type of base vocabulary, which they have to do to make the preliminary encoding for each word. That type of calculation.
Is the base vocabulary trimmed at all? Like, is that a max size? Because taking the soft max over the entire vocabulary would be huge, right?
Yeah, the vocabulary has a set size, and I remember seeing that in the source code. Any questions? We are actually over time, but it's okay.
Let's move on.
Okay, so the idea with this is that it's great, it learns representations of words and sentences, but it doesn't understand the relationships between sentences, which is between sentences themselves, which is very important for a natural language understanding model. This next task, next sentence prediction, will do exactly that. So it's exactly as you see here. So in order to learn a relationship between sentences, there are two sentences, sentence A and sentence B, and the model has to put out a label of whether sentence B comes after sentence A in the original text, or whether it's just a random sentence from anywhere else. Example here, the man went to the store, he bought a gallon of milk. Well, this sentence comes after this sentence, right? In this sentence, the man went to the store, penguins are flightless, likely to be not the next sentence of that text. So with this task then allows BERT to learn the relationship between sentences, and that's the other missing piece.
So if those are generated from the massive corpus you're training on, some percentage of the non-next sentence will actually be valid next sentences, right?
Yeah.
But it's just low enough
Bad writer, right?
that
Yeah, bad writer.
no, I mean, like, there might be sentences that actually make sense to come after each other because this topic gets revisited multiple times.
Oh, I see what you mean, like false positives.
It's
You're
more
right.
like false negatives.
Because they do randomly sample
Yeah.
these not sentences. They're randomly sampled from the text, so
Right.
yeah, that could happen.
Yes.
Yeah. But it might just be like a low enough, it's likely to be low enough
Yeah.
percentage that it won't really screw up the whole.
Or access some type of regularization. Okay, what is this trained on? Well, as I mentioned before, it's trained on a large unsupervised corpus. Corpus is a large assembly of text. Wikipedia plus book corpus, these total about 4 billion words altogether. And so the targets from the tasks, while the supervised tasks are constructed from this plain text corpus. And how did it train? Hardware, 4 cloud GPUs, 16 cloud GPUs. Okay, now here's the other last important thing I want to get to, and this is also a very important part of the paper, is how can you fine-tune BERT to perform your NLP task, right? Now that you've trained this great model, great language representation model, how do you then fine-tune it to a specific NLP task?
Sorry, quick question. So does BERT base refer to the masked?
BERT base is a smaller model, BERT large is a larger model.
Okay. So then how do you, because there are two tasks, like there's the sentence prediction and the masked word, so how do you combine those together?
Each one does those tasks one at a time. So BERT base does both of them, BERT large also does both of them.
So they trained it and then it like had its weights and whatever, and then they trained it again on the other task, and then
So kind of like the idea of
they
transfer
like go back
learning.
and forth.
So like you can unfreeze the weights, and they can
Yeah.
still be trained on the second task. So they're tuned on the second task.
Do you want to like go back and forth between tasks or something, or you just do one and then you do the other and then?
My idea is that you go one after the other, but I think it's all answers all in the source code. I don't know how
So
you
if you do the transfer learning, basically, for let's say for ImageNet, the core in all the convolutions, everything that just stays the same. You just in the end it has like 2 dense layers, and you just reinitialize these 2 dense layers with just random weights, and you just retrain it. You just run your image through all the convolutions. you get your output from this whole convolutional thing, and then you take this output and you just retrain 2 dense layers to map it to your whatever
But that's like
supervised
fine-tuning,
problem.
right? Like you'd want the whole thing to have weights that are not static, that could change, right?
Yeah,
For your new
I mean,
task.
yeah, I think it's just easy to put it this way. If you look at it, you can't really have good. It's sequential. Like I would always start with the masked version and learn the masks, then move on to the sentences, because that would make sense. But you can't really start with randomly initialized weights, and I mean you can, but that's less intuitive, I'd say. If that answers the question.
Kind of learn on top of each other.
Yeah, I mean you can always go back, but it would probably help, but I wouldn't do it.
Okay.
Okay. So, in the paper, they talk about these 2 results. So BERT can be fine-tuned inexpensively, and we'll see just how inexpensive it is. And they talk about 2 results: GLUE, which is a set of different natural language understanding tasks, and SQUAD, which is a Stanford question and answer data set. And we're going to take a closer look at SQUAD in just a moment to see how BERT fine-tunes itself for that, or how we fine-tune BERT for that. And what do I mean by inexpensively? Well, it only requires 1 additional output layer. So a minimal amount of parameters are learned from scratch. That's what I mean by inexpensive. So let's take a look at what SQUAD is. So the Stanford question and answering data set. You have a paragraph of text about some topic. In this case, it's about Black Death. And then you have some questions. Right? This forms what is fed. This forms the input, the paragraph and the questions. What are the targets? Well, the targets are answers to the questions. For example, if it's about Black Death, the question is, where did the Black Death originate? Well, there are multiple answers, but one of the targets is the arid plains of Central Asia. Now, why is that? Why that particularly? Well, it's because this target comes directly from a sequence in the text. So the arid plains of Central Asia comes from directly from a part of the text. So it's like when we were kids and we gave a question and we just copied directly from the paragraph and put it in there. And this is meant to be feasible for a machine learning model to learn. And that's important that the answer comes directly from the text, because that will play a role in how BERT is fine-tuned. Here is how BERT is fine-tuned for SQUAD. In the input, as we had before, is the question input and the paragraph. And they're separated by a separator token. And then you also have this class token, which isn't really used in this one. And so these tokens for the question and the paragraph are then fed through this entire network. And then the paragraph, the paragraph tokens, these are the learned representations of the paragraph tokens. Right? So those are going to be where your answer comes from. Now, what does BERT have to learn? Well, it has to learn exactly where in the paragraph the answer is. So it has to learn the start, it has to learn the end. And that's exactly what BERT does. It learns all that's on top of the BERT model for the SQUAD. Only 2 new vectors need to be learned from scratch: a start vector and an end vector. And these start vectors will determine where it starts, where the answer starts in the paragraph. And then these start and end vectors will interact with the learned representation to determine where the answer starts and ends. I'm being a little light on the details. That's the general gist of how easy fine-tuning is for BERT to the SQUAD data set. Any questions about this?
So it's learning the position in the text. So is it learning a vector or the position itself?
So it's a bit complicated. I'll just talk about it briefly. I know we're going to get to the discussion. So what BERT does is that it learns a start vector and learns an end vector. And then it goes through all these different vector representations of these words. And it sees which one of these vectors is most similar to the start vector. That's when it starts. And then it goes on until you see a vector that is the most similar to the end vector. And that's where it ends.
So it can only pull out like a particular like sequence.
Yes, it can jump. And in the original question, these answers didn't jump around, right? They were one specific sequence. So a very lazy student.
So a quick question about the task. It's given a paragraph and a question.
Yes.
So that's not an information retrieval. Go find the answer everywhere else. It's
Right.
given the paragraph.
Yes.
Just it boils down to finding the end and start tokens.
Yes, the answer in the paragraph. It's explicit in the paragraph. You have
Yeah.
a relevant question? to this?
Yeah. Do you fine tune all the layers, or do
Yeah.
you just do
No, you only fine tune the
Yeah.
additional layer,
Okay.
right? The additional layer that you put on top of this.
So it's basically not fine tuning. You're
Yeah.
only training.
the training a new layer?
the
You're
new
only
layer,
training like the additional layer that you put in the very end.
which is one type of fine tuning.
I think it is fine-tuning all the parameters.
No way. In the paper, it says that it only learns
data
like
enough to fine-tune
parameters
those
of fraction. That was like the main focus of the paper.
And they don't do a good job in explaining the model within the paper. They just cite another paper, how they do it, and in this paper they just cite another paper again. So you have to go like two papers deep just to understand what they're doing.
And
And in the paper, what they cited, the important thing they said, for the transfer learning, all they do is take as an input the output from the last attention layer. This is
Okay.
what they do, the transfer learning. They take the output from the last attention layer, add a linear layer behind it, and then voila.
So practically speaking, if I wanted to use this tomorrow
Yes.
at work, I would just train the head and not worry about the encoder mechanism.
Yes,
at all.
train the very last
The very last
layer that
That I
relates
add
to
on.
your specific task.
Yeah.
Right. Okay, those are all great questions. Thanks for these clarifications. Okay, let's move on. Just some quick results I want to show you about BERT. It does really well. Right, and yeah, it beats all the other state-of-the-art models, which
Wait,
are
wait,
also
where
making.
it beats people?
Yes.
Yeah. Well, they beat people at they beat people at this stage. So, well, sort of. They match people. Sort of beat people at this stage.
That makes me feel less good about people.
So that's the swap performance. And really quickly, I want to show you also the glue performance. This is the other benchmark that it showed. And I just want to highlight to you, without going into detail, that again, BERT does really well. It beats all the state-of-the-art results, especially Elmo and OpenAI GPT, which they kind of roast all throughout the paper. So.
Not nice.
So I wanna just conclude by saying a couple of final significant words. So this comes from the paper. The BERT author says the really amazing unexpected results that when they go from a big model, BERT base, to a really big model, BERT large, you get incredible, huge improvements even on small data sets. So small data sets related to natural language tasks of less than 5,000 labeled examples. So the BERT author claims that they can essentially generalize this and fine-tune it to do very well on small data sets, on tasks with very small data sets, which, if true, is very interesting, very, very helpful.
They should double it.
Do they give any intuition why?
Intuition why?
That's how.
Why? I guess there's a lot of parameters.
No, but the key question there, I think, is why is it not why isn't it just memorizing? Right? Like, why are you not massively overtrained? Like, the reason why we don't throw massive models at things is because you're going to overfit times infinity. So being able to use a 300 million parameter model on a task that should not have enough data points as parameters.
But Mike, to the question I asked earlier, it's not really, like they're just extracting the features out and then training the head. So it's really just like they're extracting a bunch of features, creating a new data set.
No. So for that, for the actual encoder, for the BERT model, there are actual parameters because it's half of the, if you remember. So that. So
But it's not learning a task, is your point.
Yeah.
Yeah, it's not learning a task completely from scratch. Putting 340 million all for this task.
Yeah, it's just learning 300 million just for a representation.
Yes.
Yeah.
On Wikipedia. 300 million.
Which we have a
learn
lot
Wikipedia.
of data for.
Yeah.
Yes.
Which is why this makes sense. Like a statement.
So this means that human language really needs more parameters even than.
Well, it means that the representations of human language need a million.
Because
tons of
humans
millions
don't
of
do as well
They need less parameters.
Okay.
They should double it again and then see if it improves.
600 million parameters. Just to end off, a couple of concluding remarks that I got from this paper is that BERT is a very strong pre-trained model that uses bidirectional transformers, which are essentially the transformer encoders of the original transformer paper. And the important part was that it was trained on two novel language modeling tasks, the mass language modeling and the next sentence prediction. And those were crucial to the BERT success. The other thing is that the whole point of BERT is that it can be fine-tuned to beat many state-of-the-art results on various NLP tasks. Now this paper was long and involved, and the source code was even longer, so there are a lot of things I did not explain. For example, the mechanics of BERT pre-training, which we talked about. There's some questions about that earlier, about how how do you get it to spit out the mass in a mass language model task? How do you get it to do this? Right? I didn't explain that. And I'll refer you to the source code on GitHub, so the answers are all there. If you look hard enough. They're just hidden very, very well. How to fine-tune BERT to other NLP tasks. I talked about Squad, but there's at least 8 different NLP tasks in the glue benchmark. And then they have their own fine-tunings. And for that, and finally, evaluation studies, which Gordon mentioned in his discussion points, which are critical evaluation of BERT methodology. So when they roast OpenAI GPT and they roast Elmo, they try to do it critically, in the sense that they try to, every single methodology, or nearly every single methodology they use in BERT, they try to compare that to OpenAI GPT, which OpenAI GPT uses a left to right transformer. And in the application studies, they compare the effects, for example, of a bidirectional transformer to OpenAI GPT, keeping all the other parameters relatively constant. Well, I'm just finished. So,